Today we're going to be talking about parametric equations. So parametric equations give you an x position in terms of time and a y position in terms of time. So for defining it, typically you're going to have an x equation, which is equal to your horizontal position. And you're going to have a y equation, which is going to give you your vertical position. So if you take the derivatives of those, the derivative of x is going to give you the velocity in the x direction. So this is going to be your horizontal velocity. And just as a convention, if this is positive, it means you're moving to the right. If it's negative, that means you're moving, the whatever is moving to the left. The derivative of the y is going to be the velocity in the y direction. So we'll call that the vertical velocity. And then again, as convention, if it is positive, it's moving up. If it's negative, it's moving down. And then lastly, the second derivative of position, the first derivative of velocity is going to be your acceleration. Okay, so these will be your acceleration. So some other definitions. So this is going to give you the velocities broken up into parts. So if you want the speed, that's going to be the square root of the velocity in the x squared plus the velocity in the y squared. So sometimes you'll be asked to write the equation, sometimes, and usually it'll be a specific location. In parametric, if we want to find dy dx, okay, so notice there's no t here. If I want to find the slope or dy dx, that's going to be dy dt over dx dt. Now here's the weirdest one with parametric. The second derivative, dy dx, so the second derivative in parametric is going to be d dt of dy dx all over dx dt. So I'm going to explain that one a little bit, and then we'll come back to the notes here. So I'm just going to do a quick explanation. I'll include a link in this video right here with another explanation for this. So really, this notation says I want d dx of dy dx. And that's why this notation is the way it is. It's the derivative with respect to x of dy dx. Well, there's no t here. So if I want the derivative with respect to t, I need to introduce a t into the problem. So I'm going to do that here. Okay, and then this just ends up being the reciprocal. So we're taking the derivative with respect to t of dy dx, which in this case is going to be in terms of t, divided by dx dt. So again, I've included another explanation for this. Okay, so our first example, we have x is t squared and y is t plus 1. We're going to plot these points, and we're just going to do this all by hand. So we're going to have a table of values with t, x, and y. And my t's are going to go from -3 to +3. Then we're going to take those and plug it in to each of the equations. So I'm just going to do an equation at a time. So my x's are going to be squared. So -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, and then we have 1, 4, and 9. Then we're going to have t plus 1. So we're just going to add 1 to all these. So we're going to have -2, -1, 0, 1, 2, 3, and 4. Now when we graph, we're only graphing these coordinates, this x coordinate, this y coordinate. So my x values go from +9 down to 0. So I have no negative x values. So we'll just graph. So we have an x value at 9, up or down at -2. We're at a +4, -1. We're at 1, 0, 0, 1, 1, 2, 4, 3, and 9, up at 4. So this ends up being a sideways parabola, indicating the direction of motion. As time increased, we started at this point and went around this way. So we'll mark that on our graph, because time is a feature here, it's just not necessarily shown graphically. Now what we're going to do is find the equation not in terms of t. So by eliminating the parameter, and there's different ways to do this, what I'm going to do is just a simple substitution. So x equals t squared, y equals t plus 1. I'm going to solve this for t, and then take that and plug this in for this t. So x is going to be y minus 1 squared. So this is where the sideways parabola is coming from in this example. So our position, and these are all going to be vectors. So we're going to use the vector notation. So the position is going to be t squared, t plus 1. Our velocity is going to be the derivative of that. So derivative of t is 2t, derivative of t plus 1 is just 1. And then the acceleration is going to be the derivative of this. So this is going to be 2 and 0. The speed is going to be the square root, and we're going to look at the velocity. It's going to be the dx dt squared plus dy dt squared, and then the square root of that. Last, or not last, the equation of the tangent line. So anytime we want the equation of a tangent line, we need two things. We need a point, and we need a slope. The point at t equals 1, we can go back up to the chart. When t was 1, our x value was 1 and our y value was 2. Or you could use the position formulas to do that as well. The slope is always dy dx. Now this can come in different ways. For parametric, that's dy dt over dx dt. So my derivative of the y was 1. My derivative of the x was 2t. And then we want this at t equals 1. So that's going to be 1 over 2 times 1, or 1/2. So then my equation is going to be y minus 2 equals 1/2 x minus 1. We'll put our point and our slope, and we can leave it just like that. The second derivative here is going to be d dt of dy dx over dx dt. So the derivative with respect to t of dy dx, which we found was 1 over 2t, over dx dt, which is 2t. So we take this derivative. The derivative of 1 over 2t is going to be negative 1 over 2t squared times the derivative of the inside, so 2 over 2t. And we can simplify this if we want. So this is going to be a negative 2 over 4t squared over 2t. So this is going to be, the 2's can cancel, and then we can combine this. So this is going to be a negative 1 over 4t cubed if you want to simplify, but we don't necessarily need to do that. So for next example, we want to find all values of the parameter t at which the curve x equals this and y equals this has a tangent line that is horizontal and vertical. So dy dx is equal to dy dt over dx dt. So for each of these, just like any slope since Algebra 1, if the numerator of the slope is 0, we have a horizontal line. If the denominator is 0, then we have a vertical line. So for this, we need dy dt to equal 0. Here we want dx dt to equal 0. So we're just going to deal with each of these equations separately. So dy dt is going to be 2t plus 1. We want that to equal 0. So that's going to be when t is equal to negative 1/2. Here, we'll take the derivative of x. So this is going to be 6x squared minus t plus 24 equals 0. Well, here we're going to have to factor. So I'm going to first pull out a 6, which is going to leave me with t squared minus 5t plus equals 0. So 6 times, this is going to factor to minus 4 and minus 1. So this one's going to be 0 when t is 4 and when t is equal to 1. Our next parametric equation, x equals 1 plus cosine t and y equals 3 minus sine t. If our function includes trig, we are going to use our good old identity that sine squared, I'll go with t, sine squared t plus cosine squared t equals 1. Sine squared plus cosine squared always equals 1. So I'm going to take each of these equations and solve them. So here, x minus 1 is going to equal cosine of t. which means x minus 1 squared equals cosine squared t. And then we'll do the same thing with this one. So y minus 3 equals negative sine of t. So y minus 3 squared equals sine squared t. And then we're going to take those and replace it here. So sine squared t gets replaced with y minus 3 squared. The cosine gets replaced with x minus 1 squared equals 1. So this equation is a circle. It's a circle with the center at 3, 1. Nope, that's 1. 1, 3. And then the radius is 1. So I can graph that. So we'll put a center at 1, 3. And then we just have a radius of 1, so just 1 in each direction. To figure out the direction, I'm going to plug in a few points. I'm going to start with 0. So if I plug in 0 into my x equation, that's going to be 1 plus cosine of 0. Well, that's going to be 2. So that's this point here. Let's say I go to t equals pi over 2. Well, that's going to be 1 plus cosine pi over 2, which is going to be 1. So now we need to figure out, is that this x value of 1 or this x value of 1? So I'm going to plug the y in there at t equals pi over 2. In the y equation, that's going to be 3 minus sine pi over 2. Sine of pi over 2 is 0, so this is going to be 3. So my second point was this one, which means we're going this direction. The velocity vector is just going to be the derivative of each of those. So the derivative of 1 plus cosine is going to be a negative sine of t. The derivative of 3 minus sine t is going to be a negative cosine of t. And that's all we have to do. For the tangent line, again, we need a point and a slope. So for the point, we're going to plug 3 pi over 4 into each of our equations. So the x is going to be 1 plus cosine 3 pi over 4. So at 3 pi over 4, our cosine value is negative root 2 over 2. The y is going to be 3 minus sine 3 pi over 4, which is also going to be negative root 2 over 2. So this is going to be 3, oh no, y, second quadrant, is going to be positive root 2 over 2. The slope is always dy dx, which is going to be dy dt over dx dt, which we already figured out here. So my change in y is going to be negative cosine. My change in x is negative sine. So you can plug it in here, or we can look at this is the same as positive cotangent t, or leave it here. So this is going to be the cotangent at 3 pi over 4. Tangent at 3 pi over 4 is going to be negative 1, which means cotangent is also going to be negative 1. So we'll take all this information and put it in our formula. So our equation of the line is going to be y minus the y value equals our slope times x minus 1 minus root 2 over 2. Sorry for the mess. So it's just y minus the y coordinate equals -1 times x minus the x coordinate. Last thing we're going to do here is the second derivative. So this again is d dt of dy dx over dx dt. So this is going to be d dt of our first derivative, which was cotangent, over dx dt, which is still negative sine. So the derivative of cotangent is a negative cosecant squared over a negative sine squared, which you can again simplify if you want to, or just leave it like that. So we have another one involving sine and cosine. So we're going to eliminate the parameter. So if x is 2 cosine of t, that means x over 2 is equal to cosine of t, which means x squared over 4 is equal to cosine squared. And then we'll do the same thing here. Y over 5 equals sine of t. So square that. Y squared over 25 gives us sine squared t. So sine squared t plus cosine squared t equals 1, which means y squared over 25 plus x squared over 4 equals 1. All right, so you have to think all the way back to algebra 2. This is the graph of an ellipse. So I'm going to graph it. So this ellipse, and there's major axis, minor axis, all that stuff, but I just look at this, and so in x, this is centered at the origin because we don't have a plus or minus with the x and y. So in the x direction, we're going to go to the square root of 4, which is 2. In the y direction, we're going to go the square root of 25. And then there's our ellipse. Then to figure out the change in motion, I'm again going to plug in values. So I'm going to start with 0 and figure out what the x is. So that would mean x equals 2 cosine of 0. Cosine of 0 is 1, so this is 2. So my starting point here is this one, because that's the only point that has an x coordinate of 2. So when t equals pi over 2, my x equals 2 cosine pi over 2, which is 0. So is it this point or is it this point? So we'll plug it into the y. So sine of pi over 2 is 1, so this is 2. Sorry, that's a 5, which makes this 5, which gives me this point here. So my direction, again, goes this way. And that should kind of make sense since it's going to follow a unit circle pattern since there's no negative or anything there. The speed of the particle at t equals pi over 3. So this is going to be the square root of the derivative of x, which is going to be a -2 sine t, but I'm going to replace the t with pi over 3 squared, plus the derivative of y, which is going to be 5 cosine. Instead of t, we're going to have pi over 3 squared. And we're just going to leave it like that. You can simplify it again, but we don't need to. Our acceleration vector. Okay, so the derivative of 2 cosine was -2 sine, which means this derivative is -2 cosine. And then our derivative of sine was 5 cosine, which means the derivative of that is a negative 5 sine t. And then the derivative at pi over 3. So I'm going to refer back to this guy here. So dy dt over dx dt evaluated at t equals pi over 3 is going to be 5 cosine pi over 3 over negative 2 sine pi over 3. And we can leave it like that, or you can simplify it. If we simplify, we're going to have 5 times 1/2 over negative 2 times root 3 over 2, which gets us negative 5 over 2 root 3 when you do the simplifying there. So a particle moves in the xy plane so that its velocity vector is t squared and sine pi t. The particle's position vector at t equals 0 is 1, 0. What is the position vector of the particle when t equals 3? So our position, and I'm just going to use s, is going to be the antiderivative of the velocity. So the antiderivative of t squared is going to be 1/3 t cubed plus c. The antiderivative of sine. So what would you take the derivative of to get sine? Well, you take the derivative of cosine, but the derivative of cosine is negative sine, so this is going to be negative cosine pi t. But again, if I take this derivative, I'd multiply by pi. So we'll divide that out. So if I take this derivative, we have a positive sine pi t times pi. So we're good. Plus c. In this case, I'm going to make it a plus d since I've already used c. Now we have to find the specific x's and y's, or the specific c's and d's. So to do that, we're going to use this information here. So I'm going to do this individually. So when t is 0, our x-coordinate is 1. So 1 is going to equal 1/3 times 0 cubed plus c, which means my c is just 1, so that goes away. This one, when t is 0, we get 0 equals negative 1 over pi cosine pi times 0 plus d. Cosine of 0 is 1. So this is going to be negative 1 over pi times 1, which means our d is a positive 1 over pi. So now we will write the particular solution. With our new known values. And then what's the position for 3? I'm going to take this. So this is going to be 1/3 times 3 cubed plus 1. And negative 1 over pi cosine 3 pi plus 1 over pi. So you can leave it like this or simplify. So this is going to be 27 divided by 3 is 9, plus 1 makes that 10. Cosine 3 pi is the same as cosine of pi, which is going to be a negative 1. So we're going to have negative 1 times this, which will make it a positive 1 over pi, plus 1 over pi makes it 2 over pi. For question 6, A curve C is defined by the parametric equations x equals t squared minus 4t plus 1 and y equals t cubed. We're going to write the equation of the tangent line at negative 227. So what do we need? A point and a slope. We've got the point. The slope, dy dx, is dy dt over dx dt. So dy dt is 3t squared. Dx dt is 2t minus 4. We want this at t equals, we don't have what t equals. We have what x and what y are. So we're going to use those, and I can use either equation. I look at this, the y seems to make sense in my head, but you can use either of them. But if 27 equals t cubed, what's our t value? T is 3 there. So t is 3. So we have 3 times 3 squared, so 3 times 9 is 27. 6 minus 4 is 2. And then we write the equation of the tangent line. So we're going to have y minus 27 equals 27 over 2 x plus 2. Our next example, as Adam Ant crawls along the xy plane, his position is given by those two equations. So we're going to plot this in the calculator, and you're given the window here. So we need to take our calculator and put it into parametric mode. So we're going to go to mode, parametric. You should always be in radians for calculus. So then we're just going to enter these in. 4t cosine t, and then 0.3t plus 2 sine 2t. For our window, we're going to go from 0 to 4 pi. Our t step, the smaller you make this, the slower it will graph. So 0.1 is fine there. Our x's min and max is going to be negative 5 to 5. And for our y's, we're going to go from negative 2 to 5. So let's watch our ant go. There he goes. So now we'll come back to the calculator in a moment. We're going to find the equations for dx dt, dy dt, and dy dx. So starting with x, this is a product, so we need to do the product rule. So the derivative of 0.4t is 0.4. This is going to be a negative, and I'm going to bring the 4t here with me, negative sine t. dy dt, we'll just add those derivatives together. So we're going to have 0.3 minus 2 cosine 2t times 2, which will make this 0.3 minus 4 cosine 2t. Then we just combine them for dy dx. dy dx is going to be dy dt over dx dt. the next thing we're going to do is find dx dt, dy dt, and dy dx at t equals 6. And we could certainly plug each of these into these equations, but if we're using our calculator anyway, we can use the calculator to find those values for us. So on the calculator, find a not shiny spot, there we go. On our graph, if we go to second calc, our options are dy dx, dy dt, and dx dt. So we're just going to do each of these. So dx dt, and then we're going to type in 6 and hit enter. So we get 1.055. Calculus is always 3 decimal places. Second calc, dy dt when t equals 6. And we get 3.675. Second calc, dy dx at 6 is 3.485. Okay, so those again, 1.055, 3.675, and 3.485. Okay, for number 8, x is equal to natural log of t and y is equal to e of t. What is the equation of the tangent line at t equals 12? So let's find our point. So x is going to be the natural log of 12. Y is going to be e to the 12. Well, if you look at our equations right now, that's our y, that's our x. These are each in point slope. So it's not going to be that one. Here, e to the 12, that one looks okay. That one's probably not it. This one could be, this one's out. Well, this is a plus, so really, we can tell right away, but let's go ahead and finish it off. But a test-taking strategy is to eliminate answers as you go. So this is the only one that has the correct points, but let's make sure the slope is right. So the slope is going to be dy dt over dx dt. So the derivative of e to the t is e to the t. Derivative of natural log is 1 over t. So this is going to be t e to the t. So if I plug in 12, we get 12 e to the 12, which does match our thought. Now we're going to look at an actual AP question from 2012. So it says, for t is greater than 0, a particle moving along a curve at time t, x of t, y of t. At t equals 2, the particle's position is 1, 5, and it is known that dx dt is t plus 2, square root of t plus 2 over e to the t, and dy dt is sine squared t. So it says, is the horizontal movement of the particle to the left or to the right of t equals 2? Explain your answer. So horizontal is going to be our x. So we're going to look at dx dt when t equals 2. So that's going to be the square root of 2 plus 2 over e to the 2. Well, I don't even have to plug this into the calculator to know this is a positive number, and that's all I care about. I don't care about what the actual number is, I care about what its sign is. So this is going to be moving to the right, because that's greater than 0. So we're just going to say right, because dx dt is greater than 0. Second part of the question, find the slope at t equals 2. So that's going to be dy dt over dx dt. So that's just this over this evaluated at 2. So we're going to have sine squared 2 all over the square root of 2 plus 2 over e to the 2. And we're going to leave it just like that. As silly as it seems, we have evaluated the derivative at the point. So we will leave it just like that because we don't want to accidentally type it in our calculator wrong and get the wrong answer. This is an acceptable answer for College Board. The next one, find the speed at 4 and acceleration at 4. So our speed is going to be the square root. It's going to be this squared plus this squared, and we're going to plug in 4 for t. So it's going to be the square root of 4 plus 2 over e to the 4 squared plus sine squared 4 squared. And again, we're going to leave it just like that. The acceleration vector at t equals 4 is going to be the derivative of dx dt evaluated at t equals 4 and the derivative of y evaluated at 4. Okay, here you can take these derivatives, but we don't want the equation, we just want the value. So we're going to use the calculator to do that. So we're just going to go back to our home screen here. We're going to do second F2, and we want the numerical derivative. So we want d dx. Ooh, I'm still in parametric mode. Well, that's fine. But you can go back to function mode as well. So we want the square root of t plus 2 over e to the t, and we want to evaluate this at t equals 4. So that's a negative 0.041. So there's our 3 decimals. You can do more, but don't do less. ddt of sine t, and we have to square that, so make sure that you put parentheses around sine of t, then square it, and again we want this at 4, so we get 0.989, and that is our velocity, our acceleration vector. So that is parametric equations.